Hello everyone. I hope you are doing very well. So hello student. So I am Brijesh Kumar and today we are going to start day 26 of our JEE 45 days crash course. So today we are going to cover D and F block elements. So let's begin with the session and this is going to be very interesting. You can see the syllabus for transition elements, or you can say D and F block elements. That means syllabus for transition and inner transition elements. D block is named as transition elements and F block is named as inner transition elements. Okay, this is the syllabus. You can see this is the syllabus for inner transition elements. So let's begin with the session. This is the approx weightage. First of all, let's go through it. So you can see the chapter is D and F block elements, and in the previous JEE exams you can see one or two questions are asked from this chapter. So you can see the topics to be covered today. So we are going to cover occurrence and characteristics of D block elements. Then we will be covering transition elements, electronic configuration, general electronic configuration, general trends of ionization enthalpy, oxidation state and atomic radii, color, catalytic behavior, magnetic properties, complex formation, interstitial compounds and alloys formation. After that, we will be discussing preparation properties and uses of K2Cr2O7 and KMnO4 and KMnO4, potassium permanganate or potassium dichromate. Both we will be discussing. Okay, then we will be discussing inner transition elements, that means lanthanoids and actinoids, 4F series and 5F series, and after that we will check the relevancy, that means we will discuss some important questions for JEE exams. So let's begin with the session. You can see here this is the periodic table. First of all, let's go through it and let's understand where are the D block elements are actually present in the periodic table. So you can see in this periodic table we have 118 elements, and out of these 118 elements you can see these 118 elements actually divided into 4 blocks. One is S block. You can see this one is S block. You can see from 13 to 18 this one is P block, right? This group 3 to group 12 is named as D block, and inside the D block actually F block is present. That's why D block is named as transition elements, but F block is named as inner transition elements because the F block elements are present inside the D block. You can see single star after lanthanum. This is the lanthanoid series, and after actinium, this is the actinoid series. You can see from group 3 to group 12, and it starts from 4th period, but this is named as 3D series. Why 3D series? Because the filling of electron takes place in 3D orbital. You can see here, right? Okay, let's move to the next one. This series is named as what? 4D series, right, of 5th period. This is 5D series of 6th period, and this is 6D series of 7th period, right? So we have D block, P block, F block and S block. S and P block are named as representative elements as well. And today we are going to discuss D and F block elements. A D block is named as transition elements. Why? We will be discussing, don't worry. And F block is named as inner transition elements. So let's continue with the chapter. You can see first of all the question is here, what are transition elements? What are transition elements, right? So transition elements are the elements in the D block of the periodic table, right? In D block, like scandium present, titanium present, vanadium present, yttrium present, right? This is in the 3D series, this is in the 4D series, right? So my point is here, these are named as transition elements. First point, they are present in D block elements and they are named as transition elements because they have partially filled D orbitals. If they have D1 to D9 electronic configuration, in there they have D1 to D9, that means not completely filled. Okay, getting my point? Not completely filled. If they have D1 to D9 electronic configuration in their ground state, or you can say atomic state or ionic state, that means common oxidation state, right? Then these are named, then that particular element of D block is named as transition element, right? The electronic configuration of transition elements follows a specific pattern, right? What will be the pattern? And according to the pattern we have general electronic configuration. So let's continue. You can see the occurrence and characteristics of D block elements, part 1. Transition metals have partially filled, or transition elements have partially filled d orbitals. As I told you already, d orbitals have, you can see d subshells have 5 orbitals, 1 2 3 4 and 5. So it can accommodate total of 10 electrons, right? It can accommodate total of 10 electrons, but it is not if it is completely filled, then that particular element is not named as transition element. If the d orbital, if the d orbitals are partially filled, then the particular element is named as transition elements, which allow them to exhibit a wide range of oxidation state, right? Due to this partially filled nature, they can exist, they can exhibit, they can show a wide range of oxidation state, right? They are good conductor of heat and electricity, and this property, why they are good conductor of heat and electricity? Because of mobile electrons. They have mobile electrons. Mobile means like they have free electrons, right, in their metallic bonding, so let's continue. You can see here these elements tends to have high densities, right, and are usually hard and strong. They are hard, they are strong, and they have high density. Density formula you know very well, mass by volume. That means they have high mass and less volume, like this. Okay, they also tend to have lustrous appearance. That means they are shiny in nature, right? They are shiny in nature. Next point, transition metals are often found in nature in the form of ores, like you can see hematite ore. This is an iron ore. Then copper ore like chalcopyrite, zinc ore like you can see sphalerite, as well as zinc blende, right, cinnabar. These are some examples. I hope you are very much clear about the occurrence and characteristics of D block elements. Some other points you can understand, like many D block elements are important catalyst in chemical reaction. Many D block elements are important catalyst. For example, platinum is used as a catalyst in catalytic converters to reduce harmful emissions from vehicles. In Haber's process, we have catalyst, right? So we have catalyst in many processes, right? So D block elements are used as a catalyst in many processes or many chemical reactions. Okay, let's move to the next point, transition elements electronic configuration. Transition elements, again I am repeating, these are D block elements. And what about F block? F block are named as inner transition elements. Okay, so let's begin. You can see the general electronic configuration of transition elements. Transition elements, that means D block elements, have some general electronic configuration, and they can be represented as n-1, d1 to 10, and ns1 to 2. What is this n-1? n-1, d1 to 10, ns1 to 2. So you can see in n-1, d1 to 10, the electronic configuration is n-1, d1 to 10. This n-1 is named as penultimate shell, right? This n-1 is named as penultimate shell, right? Penultimate shell. And this is named as valence shell. This is valence shell, right? This is valence shell. So if n value is 4, so n-1 will be 3, right? That's why what we were calling 3D series, 4D series, and 5D series. But period number, according to this n, we can predict the period number. Suppose I am just saying this is scandium, then titanium, then vanadium, then chromium, manganese, iron, cobalt, nickel, copper, zinc, right? Atomic number 21, 22, 23, 24, 25, 26, and so on 30. So on 30. If you want to write the electronic configuration, we can start from the noble gas argon 18. Then you can write 3d1 4s2. Then similarly for this 3d2 4s2, argon 18 3d2 4s2, 3d3 4s3, 3d3 4s3, 3d3 4s2, 3d3 4s2, and so on. And for zinc, like you can write 3d10 4s2, 3d10 4s2. So what you can observe here, the general electronic configuration is very like nd 1 to 10, 1 to 10, right? N value depends on the what? N value depends on what? Not n, you can say n-1. Exactly, if you want to say, you can say n-1, d1 to 10, ns1 to 2. Okay, it will vary from 1 to 2, and n minus d1 to 10 means like the electron in penultimate shells are varying from electron 1, that means d1 to d10. Okay, like this. I hope you are getting this point. So you can apply this general electronic configuration to any of the series, 3D series, 4D series, 5D series. If you are talking about 4D series means n-1 value is 4, so n value will be 5, like this. Okay, I hope you are getting this. So here n-1 d represent the partially filled d orbitals, and ns represent the outermost s orbitals, that means outermost, that means valence shell, right? Valence shell. Except for pd, okay, palladium electronic configuration is 4d10 5s0. palladium electronic configuration we have to remember, that is 4d10 5s0 according to experimental data we have seen this. Okay, let's move to the some electronic configurations of d block elements. You can see for each and every element in each case, right, in each series, in first series that is 3d series, in second series that is 4d series, in third series that is 5d series, in fourth series that is 6d series. You can see the if I want to present the palladium electronic configuration, you can see the palladium electronic configuration. Atomic number Z is represent atomic number here, Z represent atomic number here, and you can see in 4s you can see 2 2 2, but here is 1, right? What about this chromium and what about this copper? So you know very well, in the previous classes we have covered about what we have covered about the exchange energy and stability of half filled and fully filled, right? Chromium atomic number is 24. Whenever we are writing the electronic configuration of chromium, that will be argon 18, and it should be what, for 3d4 4s2, it should be like this. But this electron get transferred to here due to the half filled, because half filled, you can say d orbital becomes half filled, and half filled electronic configuration is more stable as compared to partially filled or incompletely filled. So the stable electronic configuration of chromium is 3d5 4s1, and similarly for copper, which is 29. So for copper 29 it should be argon 18, and then you can write like 3d10 4s1, 3d10 4s1, like this. I hope you are getting this point. So you can go through each and every element, like you can see 5s2 1 1 1, then 4d, similarly for 6s, similarly for 5d, that means third series, similarly for fourth series. You can go through the electronic configuration of d block elements for each series. Let's move to the some examples, like as I told you the examples of already the examples of what, chromium and copper. Similarly you can see scandium atomic number is 21, electronic configuration will be argon 18. If you want to write 18 you can write, otherwise no need. Okay, so argon, then 3d1 4s2, then similarly you can go through this example. Iron, it should be 3d6 and 4s2. Similarly you can go through the copper, it should be 3d, if you will write, you will write like this 3d9 4s2. No, that is not stable, that is unstable, but the stable one is 3d10 4s1. This is the stable one. Okay, this is the stable one electronic configuration. What I want to say one more thing, how can you learn this? Okay, not exceptions, not copper and chromium. How can you learn others? You can learn the electronic configuration like this. Suppose you want to write the electronic configuration of titanium. Titanium atomic number is 2. So the first one you can go with D, and the second one you can go with S. Suppose you want to write the electronic configuration of scandium, right? So for scandium atomic number is what? Scandium atomic number is 21. So the first one you can go with S. Okay, first one you can go with S, and the second one you can go with D. So the electronic configuration, this is from 3d series. So if you are not remembering, like this is 3 or 4, whatever, you can write in simple like D1. Okay, this for this D2 and S2, and exactly it should be 3d2 and 4s2, and it should be 3d1 and 4s2. Okay, like this. Suppose you want to write for iron atomic number is 26, so go with S and go with D. You can write argon 18, then 3d6 and 4s2, like this. Okay, you can see argon 18, if you can see argon 18 3d6 4s2, like this. These are some examples. Let's move to the general trends and properties of the first row transition element. First row transition elements, again I am saying first row transition element means 3d series we are going to discuss. Okay, so first property we are going to discuss ionization enthalpy. You know the definition of ionization enthalpy. What is ionization enthalpy? To form ions, we have to provide energy. That means ionization enthalpy is that minimum amount of energy required to remove an electron, or you can say required to remove an outermost electron, right, from outermost shell of an isolated gaseous atom. So it refers to the energy required to remove an electron from a gaseous atom or ion. It is measured in kilojoules per mole. You can see the unit kilojoule per mole. Let's move to the variations. Okay, the general trends of ionization enthalpy. First, if you will move across the period, that means left to right, group 3 to group 12. If you will move group 3 to group 12, that is a 3d series, right? 3d series. Okay, so from left to right, the ionization enthalpy generally increases. That means with increase in atomic number, with increase in number of electrons in d orbital, with increase in number of electrons in d subshell, you can say the ionization energy also increases because of Z effective increases. If Z effective increases, it is not easy to remove electron from the outermost shell of an isolated gaseous atom. This ionization enthalpy increases due to the increased effective nuclear charge. As I told you already, Z effective experienced by the electrons, right? Okay, this increased nuclear charge attracts the electrons more strongly. If more Z effective, more attraction, that means if Z effective is more, that means electrons, like whatever electrons, like if I am talking about last cell electrons, so last cell electrons are hold strongly or are held strongly, more strongly, right? Held more strongly if Z effective is more, right? With what? With the nucleus, right? With or nucleus or by the nucleus. So between the nucleus and the last cell electrons, more electrostatic attractions are there, right? Or strong electrostatic attractions are there, so making it more difficult to remove them and resulting in a higher ionization enthalpy. Okay, so if you are moving left to right across a period in 3D series, what happens? Due to the increase in Z effective, ionization enthalpy generally increases, while some exceptions are there. This is very important. While the general trend in ionization enthalpy holds true for most of the first row transition elements means scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, iron, cobalt, nickel, copper, and zinc. That means scandium to zinc, right? So you can see here chromium and copper, right? Okay, zinc is not considered as a transition element because it has a D10 electronic configuration in its common oxidation state, as well as that means it has completely filled d orbitals in its common oxidation state as well as in ground state. Okay, what about chromium and copper? These elements, chromium have half filled, right, and copper have completely filled d orbital, which provides them with extra stability. So they have some extra stability. If they have extra stability, so as a result, the removal of an electron, if chromium electron configuration is 3d5 4s1, so it is not easy. This is half filled and this is half filled, so it is not easy to remove outermost shell electrons, right, because they are more stable as compared to other electronic configuration. Similarly, copper is 3d10, this is completely filled, and 4s1, 3d10 and 4s1, 3d 10 and 4s1, right? So as a result, the removal of an electron from these atoms requires more energy, leading to a higher ionization enthalpy compared to the neighboring elements, okay, this is all about the ionization energy trend. Let's move to the manganese example. This is again very interesting. After chromium atomic number is, you know very well, chromium atomic number is 24. Chromium atomic number is 24. If you will write the electronic configuration, it comes out to be argon 18. Then you can write 4s2 and 3d what? 3d. Tell me. You can write 4s2, 3d4, or even you can write 3d4, 4s2. But the stable electronic configuration will be 3d5, 4s1. Similarly, for copper, the electronic configuration will be argon 18 and 3d10, 4s1. And if I am going to manganese, the atomic number of manganese is 24, and for copper the atomic number is 29. For copper the atomic number is 29, or for manganese the atomic number is 25. The electronic configuration will be argon 18, 3d5, 4s2. This is completely filled, this is half filled, so it is easy to remove the electron from this outermost shell of an this manganese atom? No, definitely it requires more amount of energy, right? So manganese also show a higher ionization enthalpy than expected due to its half filled, that means D5 configuration, which provides extra stability, right? Okay, you know the reasons like exchange energy and other factors, you know very well. Let's move to the next. This is the tabular form you can see of ionization enthalpy, right? You can see scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc, right? You can see atomic number 21 to 30. You can see the electronic configuration of each and every element element, right, in their M positive, M2 positive, and M3 positive states, right? You can see M 3d1 4s2, 3d2 4s2, and so on. M positive 3d1 4s1, right? So the removal of electron is taking place from d orbital, 3d orbital, right? M2 positive 3d1, 3d2, and so on, right? In M3 positive, you can see the electronic configuration. What about the enthalpy of atomization? You can see the enthalpy of atomization values. My point is here the first ionization enthalpy, the second ionization enthalpy, and the third ionization enthalpy. Okay, so I am comparing suppose I am comparing like vanadium and chromium. So vanadium first ionization enthalpy, that means vanadium electronic configuration is nothing, that is 3d3 4s2, 3d3 4s2, and chromium electronic configuration is 3d5 4s1. That means chromium is more stable as compared to vanadium. If chromium is more stable as compared to vanadium, we require, so that means chromium requires more amount of energy to remove for the removal of an electron, right? You can see for the removal of an last cell electron. So you can see the first ionization enthalpy of vanadium is 650, but for the first ionization enthalpy of chromium is 653. That's not an issue. But for vanadium, the second ionization enthalpy, you can see that will be 1414, and for chromium it is 1492, right? And the third ionization enthalpy, you can see 2833, and for chromium it is 2990. So that's all about the ionization enthalpies values in kilojoule per mole. Okay, let's move to the next, oxidation state factor. Oxidation state, right? So you can see here oxidation state, transition elements exhibit a variety of oxidation state, right? Variable oxidation state, range of oxidation states due to the availability of their d orbitals for bonding. D has, subshell has 5 orbitals, you know very well. So d bonds, right, bonds, so it can form multiple bonds. That means it can forms I can say it can forms a range of bonds, right? That means a range of oxidation state it can show. The most common oxidation state of the first row transition elements, that means 3d series, is +2 and +3, +2 and +3, right? After the removal of 2 electrons and 3 electrons, they become stable. You can see the +2 oxidation state is the most stable for those elements as it corresponds to the loss of 2 electrons from their outermost d orbital. This is known as D2s2 configuration. Like for those have D2s2 configuration like this. However, some elements can also exhibit some higher oxidation state like +4, +5, and 6. You can see, I will show you the entire tabular form of oxidation state of 3D series. The higher oxidation state are observed when the transition elements forms covalent compounds. That means by sharing of electrons, or particularly if I am saying so, mutual sharing of electrons with the high electronegative elements such as oxygen and fluorine. You can see the maximum oxidation state of you can see in MnO4 negative. For Mn it is +7, right? So the maximum oxidation state of +7 is observed in the element manganese, which is nothing, that is MnO4 negative in MnO4 negative, which form compounds like permanganate, MnO4 negative. The oxidation state of transition elements can also vary depending on the nature of the ligands in coordination compounds. What type of ligands are attached, it also depends on the nature of the ligands, strong field ligand or weak field ligand. The next point, the oxidation state of transition elements generally increase across a period from left to right. If you are moving left to right, so what happens, oxidation state or you can say variation of oxidation state will increase, right? This trend is due to the increasing effective nuclear charge, which results in a stronger attraction between the nucleus and the outermost d electrons, So let's see, you can see as a result it becomes more difficult for the transition elements to lose electrons and achieve a higher oxidation state, right? And achieve a higher oxidation state. The maximum oxidation state is usually reached in the middle of the period around group 7 or 8. Like for manganese, you have seen the maximum oxidation state is +7, right? And it is in the middle of the element 25. Now you can see middle of the 3D series, you can see. There are some exceptions. Some exceptional cases are there. Some exceptions to the general trend of the increasing oxidation state across a period, as we are saying, like if you are moving left to right, so variation of oxidation state will increase. For example, the element copper exhibiting maximum oxidation state of +2 despite being in the middle of the period. So it cannot show it can show +1 and +2, but it cannot show +3, +4, +5 like this. This is because copper has a completely filled D10 electronic configuration. Copper has a completely filled D10 electronic configuration because the copper has electronic configuration, last cell electronic configuration, if I am telling 3D10 4s1. So it can show what? So it can show maximum +2 oxidation state, which is highly stable. Next, the element chromium. Similarly, chromium and copper are exceptions, right? So exhibit a maximum oxidation state of +6 because chromium oxidation number is 3D. Chromium atomic number is 24 and electronic configuration will be 3d4 4s2, which is unstable. So we have to write again and again 3d5 4s1. Okay, I'm talking to you so that you will never make any mistake in while writing the electronic configuration of copper, chromium, and these half filled and fully filled. Okay, so it has only 6 electrons, right? You can see, so it can lose maximum 6 electrons even though it is in the middle of the period. This is due to the half filled d5 configuration in its +6 oxidation state, which is also highly stable. Let's move to some oxidation numbers or oxidation state. You can see in Mn2O7, Mn has +7 oxidation state, right? You can see +6 oxidation state like for chromium CrO3. So from scandium to titanium to vanadium to chromium to manganese, you can see +7 is in manganese. Then the oxidation state is getting decreased. So first oxidation state increases, then it is getting decreased. You can see some compounds. Like for example, if I am talking for NiO, the oxidation state is +2. Right? If I am talking for ZNO, the oxidation state is +2. If I am talking for Cu2O, the oxidation state is +1. If I am talking for TiO2, the oxidation state is +4. Like this. And I am talking only for metals, transition metals, right? You can see scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. I am talking the oxidation state only for these elements. Let's move to the next point. That is the next trend will be the atomic radii trend. Okay, size of an atom is more, so atomic radii will be more. So let's understand. You know that we are going to discuss now trends of atomic radii in the first transition series, or you can say in the 3D series, or you can say first row transition elements, and they include scandium to zinc. That means 21 to 30. 21 to 30 atomic number. You can see first point is here, decreasing in atomic radii across the period. If you are moving left to right across a period, what happens? There will be a decrease in atomic radii. Why? You can see the atomic radii of the first row transition element generally decreases as we are moving left to right across a period in 3D series because of Z effective. If Z effective is increasing, atomic radii will decrease. If Z effective is increasing, ionization enthalpy will increase. If Z effective increases, so it will strongly attract the last shell electrons, right, towards itself, and that's not easy, right, to remove that particular electron. So this is due to the increase in Z effective nuclear charge, which attracts the electrons more strongly towards the nucleus. That's the point. Okay, I hope this is clear. So generally left to right as we are moving, atomic radii in 3D series or in first row transition element series will decrease. Next is a relatively uniform radii. The first row transition elements have relatively uniform atomic radii compared to the main group elements, right? So you can see this is because the additional electrons are being added to the same principal quantum, because again and again if you will see the electronic configuration from scandium to zinc, so it will vary from D1 to D10. It will vary from D1 to, and particularly if I am saying, so 3D1 to 3D10. So again and again electrons are adding. That means the shell number is fixed. That is third, right? So again and again the electrons are adding in case of same subshell. That is third 3D, right, in 3D orbitals. So that's why if principal quantum number is same, so the additional electrons are added here, and but due to the increase in Z effective, but increase in atomic number will give the electronic repulsions, because number of electrons will also increase. So that's the point. That's why first row transition elements have relatively uniform atomic radii. You can see the third point is influence of electronic configuration. The atomic radii of the first row transition elements actually influenced by their electronic configuration. What is the electronic configuration? Half filled, fully filled, partially filled. Elements with completely filled or half filled d orbitals, that means D10 or D5, like chromium and copper. have slightly larger atomic radii due to electronic repulsions, right? Due to electron repulsions, right? Due to the repulsions between electrons in the same subshell, because they have what we can say, number of electrons in chromium is 5. Well, 5 electrons are there, and this is one is half filled, this one is half filled. So now the next point is there are exceptions to the general trend of the decreasing atomic radii across the period. For example, the atomic radii of manganese having electronic configuration 3d5, argon 18 3d5 4s2, and iron electronic configuration will be 3d6 4s2 and argon 18 also, are larger than that of chromium having electronic configuration stable electronic configuration argon 18 3d5 4s1 due to the presence of additional electron in 3d subshell. If more electrons are there, definitely electronic repulsion will increase. If more electronic repulsions, definitely atomic radii will increase, right? Due to more electronic repulsion. So nothing is the reason is here more electronic repulsion. So what you can write, more electron repulsion. If more electron repulsion will takes place, definitely atomic radii will increase. The next interesting point is here color. They have partially filled d orbitals in transition elements. If partially filled d orbitals are there, so maybe paired or unpaired electrons will be there. So transition elements exhibit a wide range of colors. Wide range of colors you can see, like configuration 3d0 in case of scandium 3 positive, that means after the loss of 3 electrons, because simple scandium has electronic configuration 3d1 4s2. So after the removal of these 3 electrons, it will become scandium 3 positive ion, and it is colorless because it has no electron. Similarly 3d0 Ti4 positive, colorless, but 3d1 due to this 1, right, it will show color purple. Okay, similarly you can see other examples. So this is due to the color is due to the presence of partially filled d orbitals which can absorb some light and reflect light at different wavelengths, and we will see the with your reasons. Okay, and you can see the different colors. For example, copper you can see appears blue, chromium appears blue. So copper you can see here Cu2 positive appears blue. For example, chromium 2 positive you can see it is appearing blue, and iron appears blue. So iron appears yellow, right? For example, Fe3 positive appears yellow, Fe2 positive appears green, right? So that is the point here. Let's move to the next point, that is the catalytic behavior. Initially we were discussing some properties in that part. As I told you, like platinum act as a catalyst, iron act as a catalyst, vanadium act as a catalyst. Similarly, what about this catalytic behavior? So transition elements are known definitely for their catalytic activity, right? They can act as a catalyst in various type of chemical reactions. For example, vanadium, initially I was talking about the examples of platinum, and now I am giving some example of vanadium. Vanadium is used as a catalyst in the production of sulfuric acid. So there are some processes like Haber's process, Ostwald process. So we will be discussing them. So this is all about the catalytic behavior. Next is magnetic property. Whenever in any question, if you want to calculate the magnetic moment, so you have to use this formula, mu is equal to under root n plus 2, where n is the number of unpaired electrons Bohr magneton. So you can see many transition elements are paramagnetic due to the presence of unpaired electrons, but some are ferromagnetic as well, right? This is due to the presence of unpaired electrons in their d orbitals. Paramagnetic substances are weakly attracted, and ferromagnetic substances are strongly attracted in the presence of external magnetic field. And you know, if paramagnetic substance can lose their magnetism, but ferromagnetic substance can retain their magnetism, right? Ferromagnetic substances are strongly attracted and can retain their magnetism. You can see the tabular form here. So in this tabular form, you can see the iron is Sc3 positive. It is 3d0 configuration, because 3d1 4s2 is the electronic configuration of scandium, and after the loss of 3 electrons, it will show 3d0 electronic configuration. And because it has no unpaired electrons, so magnetic moment will be 0 and calculated as well as observed. So both data is here. You can see similarly Ti for titanium 1. So you can put the value 1 plus 2 3, and under root 3. Under root 3 means 1.732. So 1.732 Bohr magneton should be the dipole moment of what? Ti3 positive ion. So what is calculated is 1.73 and observed is 1.75. So not a big difference, right? Similarly, you can see the other examples. Like Ni2 positive 3d8 and 2 unpaired electrons are there, because 3d8 is what? 1 2 3 4 and 5. So you know very well how to fill electrons. So 3d8, so you have to fill 1 2 3 4 5, then 6 7 and then 8, right? Then 8. So you can see only 2 electrons are there which are unpaired. So 2 unpaired electrons, that means 2.84. If you will use this formula where n value is 2, so you can put this formula 2 plus 2 4 to the 8, so it will comes out to be under root 8. You can calculate the under root 8 value, you will get 2.84 calculated, and the range of observed magnetic moment will be 2.9 to 3.4, right? That's very interesting part. So magnetic property, this is all about the magnetic properties. Next is complex formation. Complex formation, it can form a large complexes, right? Transition elements can form large complexes. They have the ability to form complex compounds. They can form coordination compounds. They can form coordination complexes by donating their d orbitals electrons to the ligands, right? So they can accept electrons also in their d orbitals from ligands, right? From ligands. So that's the point here. I want to go to the next point. Okay, so like you can see, these complexes have unique properties and are often highly colored. And for example, the complex found between copper and ammonia is deep blue in color, right? If you will see the copper and ammonia complex, so which will be deep blue in color. That's very interesting. Next is interstitial compounds. Okay, interstitial compounds, so transition metal can form definitely interstitial compounds, because these compounds occur when small atoms or molecules occupy the interstitial space between the metal atoms. So metal atoms have some lattice structure. Whenever suppose this is the one, I am giving some examples, like this is a part of a lattice, and this site that is inside this is the this empty space is interstitial site. Okay, this empty space is interstitial site. If this is the interstitial site and any like metal atom, so these compounds occur when small atoms or molecules. So if any small atom or molecule will occupy the interstitial site between these metal atoms, so you will get interstitial compounds. So definitely transition elements can form interstitial compounds. Some small elements like hydrogen, oxygen, like this. Let's move to the next. Interstitial compounds can have unique properties such as high hardness. So due to the filling of this empty space, now what happens if something is hollow and something is like solid? So hollow thing you can break easily, like if hollow stick is here, right? If hollow pen is here, you can break easily. But if it is solid, so you require more amount of energy to break this, right? So definitely interstitial compounds, if the space, the interstitial space that is present, right, in the lattice of metal atoms, so what happens that if that is filled with small atoms, right, small atoms, so definitely their properties will change and they becomes hard, right, such as high hardness and high melting point. Okay, like titanium can form interstitial compounds with hydrogen and carbon. Titanium can form interstitial compounds with hydrogen and carbon, and we have to use these types of interstitial compounds because to increase the efficiency of that particular element. Like if any element is what I can say, if any metal lattice is not very hard and it has a low melting points, and we want to use that particular metal, right, in any field. So if we want to use, so we have to suppose increase, we need hard material, right, of that particular element. So we can use these type of small atoms, and they can occupy the interstitial space, and then the metal lattice becomes hard, and it become, and the melting point of that particular metal lattice becomes high. That's the point here. Okay, next one is alloys formation. They can form alloys as well. So they are widely used in the formation of alloys. Like alloys are nothing that are mixtures of two or more elements, and out of these two or more elements, at least one should be metal, at least one should be metal. That is the point here. Like so many alloys are there, like bronze, brass. These are some examples of alloys: bronze, brass, etc. Okay, so you can see definitely alloys formation is very important, and it is applicable in our daily life as well. Let's move to transition elements can improve the strength, hardness and corrosion resistance of alloys, right? And for example, steel is an alloy of iron and carbon, which contains small amounts of other transition elements as well, right? So iron is a transition element, so definitely they can form alloys. Definitely they can form alloys. Now I want to move to the next, that is the potassium dichromate preparation. All right, we will be discussing now preparation of potassium dichromate dichromate properties and uses. So potassium dichromate formula is K2Cr2O7 and dichromate ion is Cr2O7 2 negative. Cr2O7 2 negative. So let's discuss. You can see the first of all preparation. Dichromates are generally prepared from chromates. First of all, we need chromates. Okay. Chromates are obtained by the fusion of chromitor, which is nothing that is FeCr2O4 with sodium or potassium carbonate in free access of air. In free access of air. You can see the reaction. 4FeCr2O4, which is chromitor, and with the reaction with the sodium carbonate reaction is taking place. So 4FeCr2O4 plus 8Na2CO3 in the presence of air 7O2, you will get 8Na2CrO4, which is sodium chromate. So CrO4 two negative ions are what? CrO4 two negative ions are chromate ions and Cr2O7 two negative ions are dichromate ions plus 2Fe2O3 plus 8CO2. So you can see this is the balanced chemical equation. Then the balanced chemical equation becomes, if we will heat this sodium chromate in presence of acids, you will get sodium dichromate. Okay, so 2Na2CrO4 sodium chromate plus 2H positive, you will get sodium dichromate Na2Cr2O7 plus 2Na positive plus H2O. Then this Na2Cr2O7 can be converted to K2Cr2O7. So K2Cr2O7 is prepared by the reaction of sodium dichromate. This one is sodium dichromate, which is Na2Cr2O7 with the potassium chloride. So ion exchange will take place and this reaction takes place in an acidic medium. So you can see the complete reaction. Na2Cr2O7 plus 2KCl plus H2SO4. You will get K2Cr2O7. So ion exchange will take place. K2Cr2O7 plus Na2SO4 plus 2HCl. So this reaction is also an example of redox reaction, means oxidation and reduction is occurring in this reaction simultaneously. I want to move to the properties of K2Cr2O7. So we have done with the preparation of K2Cr2O7. Now I want to move to the properties of K2Cr2O7. K2Cr2O7 is nothing that is potassium dichromate. It's very interesting. It is an orange red crystalline solid and also highly soluble in water. Potassium dichromate is highly soluble in water like sodium chloride, like, and the solubility also depends on the temperature as well. Okay, so it is an orange red crystalline solid and it is highly soluble in water. It is a strong oxidizing agent. In many organic reactions we have to use potassium dichromate. Like suppose you want to convert alcohols, suppose you want to convert alcohols to carboxylic acid, so you can use strong oxidizing agent, which is nothing that is the acidified K2Cr2O7, acidified potassium dichromate you can use, and you will get carboxylic acids. You will get carboxylic acid, right? You will get carboxylic acid. If you want to convert like methanol to methanoic acid, ethanol to ethanoic acid, like this, it is stable in acidic medium but decomposes in alkaline medium. So in alkaline medium it is not stable, that means it will decompose. In alkaline means basic medium, right? Basic medium, it will decompose. Okay, alkalis are those bases which are soluble in water, you know very well. It is an ionic compounds with potassium ions like K positive. So if you will break this into ions, K2Cr2O7 will provide two types of ions. One is positive ions, that is 2K positive potassium ions, another is dichromate ions, Cr2O7 2 negative, right? You can see this is all about the what, some properties of K2Cr2O7. Now let's move to the uses of K2Cr2O7. K2Cr2O7, which is nothing that is potassium dichromate, is commonly used as an oxidizing agent in various chemical reactions. It is used in the preparation of aldehyde, ketones and carboxylic acid. I told you already with some examples, like you can convert alcohol to carboxylic acid, you can convert aldehyde to carboxylic acid, you can convert ketone to carboxylic acid with the examples of what, with the help of acidified K2Cr2O7, right? Another point we will be discussing about the KMnO4 today's as well. KMnO4 is nothing that is potassium permanganate and that's also a strong oxidizing agent. So you can see here uses of K2Cr2O7. Another uses used in the laboratory for various qualitative analysis tests, okay, and used in the manufacture of dyes, pigments and chrome tanned leather, as well as in the preparation of potassium chromate and potassium dichromate, okay, as well as in the it is also used in the preparation of potassium chromate, okay, and sodium dichromate we can prepare with this. Let's move to the structure of chromate and dichromate ion. Chromate ion is nothing that is CrO4 2 negative and dichromate ion is Cr2O7 2 negative. Definitely there is a bridge, right? You can see this oxygen is act as like bridge atom, okay. So CrO4 2 negative, very simple structure like tetrahedral structure, and similarly two tetrahedrals are joined together with the help of a single oxygen bridge atom, right? Like this. Okay, if you will get this one is like a tetrahedral, and if you will get this one is like a tetrahedral, like this. Okay, not exactly tetrahedral, distorted tetrahedral, you can say. Okay, this is about the Cr2O7 dichromate ion structure, and this is the chromate ion structure. Let's move to the next, potassium permanganate, which is nothing that is KMnO4. In ionic form, you can say K positive, it will provide K positive, and NM4 negative. MnO4 negative is nothing that is a permanganate ion, right? Permanganate ion, first of all, let's discuss the preparation. How can we prepare permanganate, or you can say potassium permanganate? Okay, so potassium permanganate, that is KMnO4, is prepared by the reaction of manganese dioxide, that means MnO2 we need, with potassium hydroxide, that means we need KOH, and an oxidizing agents like KNO3, potassium nitrate. KNO3 is a strong oxidizing agent. The reaction takes place in an KNO3 is also an oxidizing agent. The reaction takes place in alkaline medium. Okay, already base is here, KOH, so definitely alkaline medium will be there. The balanced chemical equation, you can see we need manganese dioxides 2MnO2 plus basic medium, that is 4KOH plus O2. In presence of air, you will get 2KMnO4 plus 2H2. So 2MnO2 plus 4KOH plus O2 gives 2KMnO4 plus 2H2. If you want to calculate the oxidation state, you can see the oxidation state of manganese is plus 4 here, right? And you can calculate the oxidation state of manganese is here, which is nothing that is plus 1 for potassium and X for magnesium, manganese not magnesium, and minus 8 for this equal to 0. You will get plus 7. So definitely plus 4 to plus 7 it is going. So plus 4 to plus 7 means oxidation number increases, means oxidation takes place. Oxidation takes place. Okay, let's move to the next point. That's going to be very interesting, and this reaction is also an example of redox reaction. That means in this reaction, oxidation and reduction both are occurring simultaneously, and this reaction is named as redox reaction. So this is all about the preparation of potassium permanganate. So we have done with the preparation, properties and uses of potassium dichromate. Now we have done with the preparation of potassium permanganate. So let's move to the properties of potassium permanganate. What are the properties? Potassium permanganate, and you have used this potassium permanganate, which is like a looked like a violet color, right? And after mixing in water, if you will use a very little amount, you will get like a pink color. Okay, so you have used in laboratory purposes, definitely, like potassium permanganate with Mohr salts, and potassium permanganate with oxalic acid, right, in the titration part. Okay, so KMnO4 is like a dark purple crystalline solid. It's like a dark purple crystalline solid, not violet, you can say dark purple. Okay, it is highly soluble in water. It is a strong oxidizing agent, and it is stable in alkaline medium but decomposes in acidic medium. So in acidic medium it will decompose. It is an ionic compounds with potassium ions and permanganate ions, which is MnO4 negative. So these are very simple points. Okay, KMnO4 is also used as an oxidizing agent. I will provide some uses, then I will discuss some another points. You can see the uses of KMnO4. Like it is used as an oxidizing agent in various chemical reactions. Like you can see it can also convert alcohol, aldehyde ketones to carboxylic acids, right? Alcohol to carboxylic acid, you can see, because I told you already carboxylic acid, because I told you already it is stable in what? You can see it is stable in alkaline medium. That means we need alkaline KMnO4. We need alkaline KMnO4. So whenever we want to use KMnO4 as an oxidizing agent, so we have to use alkaline KMnO4, or you can say KMnO4 in presence of KOH, KMnO4 in presence of KOH, like this. Okay, to convert alcohol to acid, but it will decompose in acidic medium. So you can see here KMnO4 is act as an oxidizing agent in various chemical reactions. Also it is used as a disinfectant and a water treatment plants, right? In water treatment chemical or water treatment plants. So to convert alcohol to carboxylic acid, what we have to use? We can use potassium dichromate, or you can say acidified potassium dichromate, and you can use KMnO4, which is nothing that is potassium permanganate, and it is stable or in alkaline medium, but it will decompose in basic medium. It is stable in alkaline medium, but it will decompose in acidic medium. Okay, it is used in the synthesis of organic compounds. You can see these are organic compounds, so definitely it is used in the preparation or synthesis of organic compounds. Used in the laboratory for redox titrations, as I told you already, redox titrations and qualitative analysis test. Also used in the manufacture of dyes, pigments and fireworks. It is not highly soluble in water, right? It is not highly soluble in water. It is used uses for the bleaching of wool, cotton, silk, silk and other textile fibers, and for the decolorization of oils as well, right? In decolorization process we can use KMnO4 as well. You can see the structure of manganate, which is nothing that is MnO4 negative, and permanganate, right? MnO4 negative, and permanganate is what? Permanganate is MnO4, okay, and negative, and this is 2 negative, okay, manganate and permanganate ion. So manganate ion has tetrahedral structure and it is like green in color, tetrahedral manganate. Mn double bond O, single bond O negative, single bond O negative, okay. Also you can write like this, okay, Mn double bond O, single bond O negative, and single bond O negative. This is like tetrahedral structure. This is like tetrahedral structure. I hope you are very much clear about this structure. Similarly, three double bonds are there with oxygen and single O negative. So this is MnO4 negative. This is also tetrahedral, but this is purple in color. This is purple in color. The color changes due to the presence of unpaired electron as well, right? Due to the presence of unpaired electron. Okay, let's move to the next one. So we have discussed the D block elements. We have discussed the D block elements. We have discussed the general electron configuration, some trends in physical properties like ionization enthalpy, like atomic radii, like color, catalytic behavior, etc. Right? Then we have discussed the preparation of K2Cr2O7, and we have discussed the preparation of KMnO4, uses and properties of K2Cr2O7, that means potassium dichromates and potassium permanganate, right? So these points are very much clear to all of you. Now we are going to discuss the F block elements, and F block elements includes two series. One is named as lanthanoids, that means 4F series, because 4F filling of electrons will take place, and the next one we will discuss the actinoids. So first of all, let's discuss the lanthanoids. Lanthanoids, so you can see the introduction to lanthanoids. The inner transition elements are a group of chemical elements located in the F block. You can see the two horizontal rows below the, what I can say, periodic table, right? These are also includes the periodic table. So these two horizontal rows are, the first one is lanthanoids and the second one is actinoids, okay. Lanthanoids, also named as lanthanides, are a series of 15 elements with atomic number ranging from 57 to 71, okay, 57 to 71. Let's move to the next, electronic configuration of lanthanides. The general electronic configuration of lanthanides varies, like xenon, which is 54, then 4F-N, N will vary, 5D1, 6S2. So 4F subshell is progressively filled with electrons as we move across the lanthanoid series. I will show the electronic configuration, okay. So you can see here the electronic configurations of lanthanoids of each and every element. So 57 is lanthanum, and 58 cerium, then you can see 59, 60, 61, and so on, and then 71, right? So La2 Lu is lutetium. So La2 Lu, you can see the electronic configuration 5D1, 6S2. So from here you can see this 1 2 3 4 5 6 7 8 9 10 11 12 13 14, these 14 elements are present in what? In lanthanoids, right? Okay, after lanthanum, so you can see the electronic configuration is 4F1, then 4F3, 4F4, 4F5, 4F6, 4F7, then 4F7, then 4F9, 4F10, like this. You have to learn this electronic configuration. You have to practice. This is the electronic configuration of lanthanoid in ground state. This is the electronic configuration of lanthanoid is +2 oxidation state. This is the electronic configuration in +3 oxidation state. Similarly, you can see the radii in picometer of Ln4 positive, Ln, and Ln3 positive. You can compare, right? And this is the electronic configuration of Ln4 positive as well, okay. So you can see the electronic configurations in different oxidation states. So what you can observe from this electronic configuration, and you can see like +2, +3, and +4. These are general oxidation state of what? These are general oxidation state of, general common oxidation state of what? You can see these are the common oxidation state of what? These are the common oxidation state of lanthanoid series, right? So you can see Ln, then you can see Ln2 positive, Ln3 positive, Ln4 positive, right? You can see in Ln2 positive, you can see Ln3 positive, and you can see Ln4 positive, and similarly you can see the radii in picometer of Ln and Ln3 positive. So the common oxidation state of lanthanoid is Ln3 positive. Sometimes some elements can show +2 and +4 as well. We will be discussing that points okay. Only electrons outside xenon core are indicated, right? So these electrons are outside the xenon core. So let's move to the next point. You can see the oxidation state of lanthanoids. Lanthanoids generally exhibit, I told you already, +3 oxidation state, which is common oxidation state due to the loss of 3 valence electrons, right? However, some lanthanoids can also exhibit what? +2 and +4. So Ln +3 is common, and sometimes you can observe Ln +2 and Ln plus 4 as well. Okay, so the stability of plus 3 oxidation state increases as we move from beginning, that means cerium, to end of the lanthanide series, that means lutetium. Okay, you can see here lanthanide contraction is a word here, that's very interesting, so listen me very carefully. Lanthanide contraction is nothing, that is the gradual decrease in the atomic and ionic radii of the lanthanoids as we move across the series. If you are moving left to right along a period, right, across a period, in 4F series you can see there is a decrease in atomic and ionic radii, and that's due to the lanthanoid contraction. This contraction is primarily attributed to the poor shielding effect. First of all, you know very well S, P, D and F, this is the shielding effect order. So F will show poor shielding effect and S will show strong shielding effect. If poor shielding effect is here, so Z effective will be more. If Z effective will be more, so attraction will be more. Attraction will be more, so definitely size will decrease. So the lanthanoid contraction has significant effects on various properties of the lanthanoids, such as their chemical reactivity and their physical characteristics. Now I want to show some important chemical reaction of the lanthanoids. You can see Ln represent lanthanoids here. When they are heated with sulfur, you will get Ln2S3 type compounds like lanthanoid sulfide. Similarly, you will get when they are burns in presence of oxygen, you will get Ln2O3, that is lanthanoid oxide. Similarly, with acids you will get hydrogen gas, they release hydrogen gas. With halogens you will get LnX3 type compound. With H2O you will get LnOH3 OH whole thrice plus H2 gas. With carbon at 2773 Kelvin, you can see the temperature, high temperature 2773 Kelvin, you will get LnC2 type. Okay, carbide type. Okay, you can see heated with nitrogen, you will get LnN, which is nitride. Okay, which is lanthanoid nitride. Okay, these are the chemical reactions of lanthanoids, common chemical reactions you can see. Now I want to introduce the next series, that is the actinoid series. Actinoid series is 5F series, right? 5F series. So in actinoid series you can see it is named as lanthanoid is named as lanthanoids because they comes after lanthanum. Similarly, actinoid series elements are named as actinoids because they comes after actinum element. Okay, so you can see the electronic configuration. The actinoids are a series of, again, you can include 14 elements. Okay, you can include 14 elements in the periodic table from atomic number 89. So actinium, after actinium 5F series starts. Okay, so you can see to atomic number 103 lawrencium. The electronic configuration of actinoid is given by the filling of 5F orbitals. That's why this series is named as 5F series, right? 5F series. You can see the electronic configuration. This is important. From here you can see questions in the previous exams. Okay, JEE exams. So you can see here actinium atomic number 89, you cannot check here, right? What you cannot see the 5F configuration. Okay, 5F is 0 here, 5F is what, 0 here. But in thorium you can see 62 7s2, and you can see M3 positive has 5F1 and M4 positive 5F0. Okay, similarly 91 92 103, you can see 14 elements are there from thorium to lawrencium, and you can see the symbols, and you have to learn these and you have to practice these electronic configuration. These are very important according to exam point of view. Similarly, you can see the electronic configuration in M4 actinoid metal. Similarly, M3 positive in +3 oxidation state and M4 positive in +4 oxidation state, right? M4 actinoids and M3 positive actinoids in +3 oxidation state, and similarly for M4 positive. In radii you can also compare in +3 oxidation state and +4 oxidation state. But you know there is a variety of oxidation states are present in a case of actinoids. Okay, so you have to remember all the oxidation states. So you can see here 5F2 6D1 7s2. Similarly for neptunium you can see 5F4 6D1 7s2. Similarly for einsteinium you can see 5F11 7s2. For you can see for curium it is 5F7 6D1 7s2. For americium you can see 5F7 7s2, like this. So you have to practice these types of electronic configuration. Now the important part is oxidation state. Say you can see the variety of oxidation state here. So the actinoids exhibit a variety and variable of oxidation state from ranging from +3 to +7. Now like not lanthanoids, they are not showing like only +3 commonly, and sometimes +2, some elements can show +4 as well. They are showing variety of oxidation state. The most common oxidation state is definitely +3, which is stable for all actinoids approach. approximately. You can see actinium, you can see then Pa, uranium, right? You can see neptunium, and like mostly you can see +3 is present. However, some actinoids can also exhibit +4 to +7. You can see for neptunium, right? And you can see Pu7 +7 oxidation state. So you can see some common oxidation state of actinoids are there, right? You can see from here to here. I hope this is clear. So you can see first the oxidation state increases, then it will start decreasing, but you have to remember the oxidation states of actinoids as well. Now let's discuss some important questions for JEE exams. You can see the first question is saying that the atomic numbers of vanadium, chromium, manganese and iron. Very easy. If the atomic number is given, we can do anything, right? That means vanadium atomic number is 23. Okay, vanadium atomic number is 23, chromium atomic number is 24, manganese atomic number is 25, iron atomic number is 26. Okay, now you can see which one of these may be expected to have the highest second ionization energies, enthalpies. First of all, you have to write the electronic configuration, then you are able to do this question. So let's see. So if you will write the electronic configuration of each and every element, if I want to write, so chromium and other elements are manganese. Okay, you can see here chromium, vanadium, chromium, manganese and iron. If I will write here, suppose, so what you can write, I told you already, this one is for S and this one is for D. So you can write 3D3 4S2. For chromium, you have to write the stable one. It comes out to be 3D4, but the stable one will be 3D5 4S1. For manganese, again 3D5 4S2. 3D5 4S2. For iron, you have to write 3D6 4S2. Okay, and the question is saying that second ionization energy, if the first electron is removed, then second electron will remove, then you will get the 3D1, and after the removal of what, 2 electrons, you will get 3D0 or 3D3. Okay, 4S2 will remove from here. Okay, you can understand with this example. So the electronic configuration of chromium, the electronic configuration of chromium is equal to 3D5 4S1. After removing 4S1 electrons, the next electron is to be removed from relatively more stable half-filled 3D5 substance. Okay, so if you will move electrons, you can see here, if you will remove 2 electrons from here, you will get 3D3. If you will remove 2 electrons, 1 electron from here, then you will get 3D5. If you will remove 1 electron from here, you will get 3D5 4S1. 3D5 4S1. If you will remove 1 electron from here, you will get 3D6 4S1. Similarly, if you will remove 1 electron from here, so you will get 3D3 4S1. My point is here, in this case, it is half filled, right? So it is easy to remove this S1, then S1, then S1 as compared to this 3D5. As compared to this 3D5. So 3D5 has highest second ionization enthalpy. That means the answer must be A. So you can see the answer is what? You can see the answer is the electronic configuration of chromium is 3D5 4S1. After removing 4S1 electron, the next electron is to be removed from the relatively more stable half-filled 3D subshell, and which will require definitely more amount of energy because it is highly stable, right, for its ionization, for the removal of next electron. So the second ionization enthalpy will be high. Let's move to the next question. The element with which of the following outer electron configuration may exhibit the largest number of oxidation state in its compounds? 3D5 4S2, 3D8 4S2, 3D7 4S2, 3D6 4S2. 3D5 4S2 definitely manganese. 3D8 4S2 definitely nickel. 3D7 definitely what? Cobalt, nickel, copper, zinc. This is cobalt, this is iron, right? So you can see the answer will be due to the presence of maximum number of unpaired electrons. In which case maximum number of unpaired electrons are there? 3D5, which is half filled. You can see 1 2 3 4 and 5. So 1 2 3 4 and 5. If we will fill electrons in each case, suppose if I am filling the electrons, in this case I have filled, in this case 3D8, if I want to fill, so you can see 1 2 3 4 and 5. In this case, if you want to fill, so you can draw 1 2 3 4 and 5. In this case, if you want to fill, you can see 1 2 3 4 and 5. So you can see number of electrons in this case 1 2 3 4 5, then 6 7 8. So number of unpaired electrons are 2 here. In this case 7. So 1 2 3 4 5 6 7. In this case number of unpaired electrons are 3, right? And 3d6. So 1 2 3 4 5 6. So in this case number of unpaired electrons are 4. And in manganese, if you want to fill 1 2 3 4 and 5, if you will fill, so it comes out to be 1 2 3 4 5. Number of unpaired electrons are 5. So more the number of unpaired electrons, and definitely it will show largest number of oxidation oxidation state. So you can see the answer will be 3d5 4s2. Manganese configuration may exhibit the largest number of oxidation state in its compounds, right, due to the presence of maximum number of unpaired electrons. The next one is the outer electron configuration of GD. GD is nothing, you can see here. If I want to show you ZD, right? So where is the GD? You can see here, GD in actinoids, in lanthanoids. Okay, so you can see the GD here. GD is gadolinium. The electronic configuration is 4f7 5d1 6s2. As I told you already, it comes out after europium. It is 4f7, but to become stable, it acquire the 4f7. It doesn't go with 4f8. It acquire the 4f7 electronic configuration, 4f7 5d1 6s2. So you have to remember these and you have to practice that, then you will get the so that these are the easy questions, right? You can see the electronic configuration of gadolinium, atomic number 64. So you will choose definitely 4f7 5d1 6s2. So what will be the answer? You can see xenon 54, then 4f7 5d1 and 6s2. Due to extra stability of half-filled 4f subshell ZD, that means gadolinium has electronic configuration is 4f7 5d1 and 6s2 instead of 4f8. Okay, let's move to the next question. Cu2O is colorless and copper 1 compounds are colorless except where color result from charge transfer. Copper 1 compounds are diamagnetic and Cu2S is black. So you have to choose incorrect statement. So Cu2O is colored because of the presence of 1 unpaired electrons. If unpaired electrons are there, definitely they will show color. If no unpaired electrons are there, if the configuration will be D0 or D10, no unpaired electrons are there, definitely they become colorless, right? They become colorless. So Cu2O is colored because of the presence of 1 unpaired electron. You can see this is the unpaired electron and which makes DD transition. So due to the DD transition, this unpaired electron will absorb energy then reflect light, right, in your, that means in visible region. Okay, so Cu2 positive, argon 3d9, and because in copper Cu2O, in Cu2O, you can see the oxidation status copper is +1 as well. Okay, oxidation status copper is +1. Okay, so here it is given. So Cu2O is colorless. So that's all about the answer of this particular question. Let's move to the next one. Which of the following arrangements does not represent? You can see V2 positive, Cr2 positive, Mn2 positive, and unpaired electrons are those electrons, Prashant. Unpaired electrons are those electrons, like suppose this is I'm writing D5. Okay, so you can see 1 2 3 4 5. So unpaired electrons are those electrons which are single electrons. So here are 5 single electrons, so these are 5 unpaired electrons. Okay, suppose I am writing like this, p subshell I am writing, so 1 2 3 4. So this becomes pair, but these two are unpaired. So this is unpaired electrons number is 2. I hope this is clear. So okay, so you can see which of the following arrangements does not represent paramagnetic behavior. This is the paramagnetic behavior. This is for ionic size. This is for stability in aqueous solution, and this is for number of oxidation state. So you have to write the electronic configuration, then you have to check. So you can see if I am going with option A, V2 positive, electronic configuration will be 3d3 4s0, electron atomic number will be 22. Chromium atomic number is 24, electronic configuration will be 3d4 4s0. So 3 unpaired electrons, 4 unpaired electrons. If you will write like this, as I told you, if you will fill electrons in D subshell, you can see 1 2 3. So how many unpaired electrons are there? 3 unpaired electrons. Mn2 positive 25, 3d5 4s0, 5 unpaired electrons. Fe2 positive 26, 3d6 4s0, 4 unpaired electrons. Hence you can say the order of number of unpaired electrons, definitely mu directly proportional to n, because mu formula is nothing, that is under root nn plus 2. If n value is increasing, so mu value is increasing. If mu value is increasing, so magnetic moment will increase, right? Definitely nature or paramagnetic nature will increase. So you can see number of unpaired electrons are more in case of 5 means manganese, then you can see 4 and 4, that means chromium and iron, then you can see 3, which is V2 positive. So this will be the order. And next one is ionic size decreases from left to right in the same period, right? So and you can see cobalt 3 positive to cobalt 2 positive, 1.97 value, and Fe3 positive to Fe2 positive, the value is 0.77, right? Scandium 3 positive is highly stable as it has 3d0 4s0 electronic configuration. It does not show +2 oxidation state. It is highly stable because now the configuration is 0 0, that means empty. And the part D, you can see the oxidation state increases as we go scandium to manganese in 3D transition series. So you can see here, you can see the next point is here, that is nothing, that is the next question. The color of the KMNO4 is due to what? ML charge transfer transition, DD transition, or ligand to metal. Metal, this is metal, and this is ligand. This is metal and this is ligand. Okay, metal to ligand, yeah, ligand to metal. So you have to remember this point. Okay, so I want to move to the next question. That is, compound A on strong heating gives two oxides of sulfur. If aqueous NaOH solution is added to the aqueous solution of a dirty green precipitate is formed which start turning brown on exposure to air. Compound A is a ferrous oxide, ferric sulfate, ferrous sulfate, or ferric oxide. So you have to choose the answer. You have to practice these questions as a homework. In context with the transition elements, which of the following statement is incorrect? A statement, in addition to the normal oxidation state, the zero oxidation state is also shown by these elements in complex. Then statement 2, in the highest oxidation states that transition metal shows basic character and form cationic complexes. Then statement C, in the highest oxidation state of first 5 transition elements, scandium to manganese, all the 4s and 3d electrons are used for bonding. And the part D statement, option D, you can say, once the D5 configuration is exceeded, the tendency to involve all the 3d electrons in bonding decreases. Next question you have to practice, knowing that the chemistry of lanthanoids Ln is dominated by its +3 oxidation state, which of the following statement is incorrect? Part A, because of the large size of the Ln3 ions, the bonding in its compounds is predominantly ionic in character. So you have to use the concepts that we have covered today and you have to practice these questions. You will get your answers. The ionic size of Ln3 decreases in general with increasing atomic number. Ln3 compounds are generally colorless, and the next one you can see here, Ln3 hydroxide are mainly basic in character. Next question you have to practice, cuprous ion is colorless while cupric ion is colored because both have half-filled p and d orbitals. Option B, cuprous ion has incomplete d orbital and cupric ion has complete d orbital. So cuprous means Cu positive and cupric means Cu2 positive. Okay, now you can write the electron configuration. Both have unpaired electron in the d orbitals, and cuprous ion has a completely filled d orbital and cupric ion has an incompletely filled d orbital. And this is the end of the session. I want to discuss one more question that we were discussing about this, like paramagnetic nature. You can see here, right? So you have to choose the does not represent. So you can see here the order will be V2 positive and Cr2 positive, Fe2 positive, then Mn2 positive. V2 positive, Cr2, so no equal sign is here. So this should be the answer, option A, right? Okay. Then you can see Ni2 positive, CO2 positive, Fe2 positive, Mn2 positive. So the answer is saying what? The answer is saying you can see here the answer is saying nothing, that is ionic size decreases from left to right in the same period. That is the point. Similarly, statement C and statement D. So this is all about this today's class. I hope you really loved the sessions. Thank you so much. This is the end of the session.